Okay, next we want to look at the concept of work. Now, work is defined as the product of the force exerted on an object and the distance the object moves in the same direction as the force. In other words, let's imagine I've got an object, let's say there's a box on the floor, and I apply a force to it. I start dragging the box across the floor. So that box will move along the floor and it'll end up over here. And it will have traveled some distance, which we can call d. And we can note that the force is pointing in the same direction that it's going. So the force is pointing to the right, the block moves over to the right, so they're pointing in the same direction. And we can calculate the work. The work is simply the product of the force times the distance. Remember, product is a fancy word in math. It just means multiply. So the work is simply the force times the distance. And that's what we end up with. Now, one thing to note is that work always involves motion. And so if, for example, if you are standing up and you push against a wall, so you're pushing really hard against a wall and you're trying to shove that wall over, but the wall doesn't move. It may feel like you're doing work because your muscles are working, your muscles are contracting, but because the wall isn't moving, absolutely no work is done on the wall. And so that's one of the things that's a little bit confusing, because you can get tired pushing against the wall, but you're not actually doing physics work on the wall. In order to have work, you have to have two things. You have to have a force, and you have to have that force acting on something as it moves over some distance. They have to happen at the same time, the force and the distance, for there to be work. Now, the quantity of work done is equal to the amount of force times the distance moved, and it's always in the direction in which the force acts that the work is calculated. So if, for example, I have a force acting on something and the object moves perpendicular, that force actually won't do any work. That force won't do any work. What happens if you have a force acting at some angle? Well, if the force is pulling up at some angle, two things are happening. Part of that force is pulling the block upwards, like it's trying to lift it off the ground, and part of the force is trying to make it slide across. And so part of the force is making it slide across. That would be a horizontal component, and then there would be a vertical component. So here's the total force. And then we could say this vertical one would be a vertical component. We could call that FV. And this would be a horizontal component, FH. And so the force would have both a horizontal part and a vertical part. Only the horizontal part would do work if this guy's moving to the right, because the vertical part is perpendicular. So any perpendicular force does no work. Now, when you think about work, basically work falls into two different categories. One category is the work done against another force, and then the other category is the work done to change the speed of an object. So here's a question. Work is done lifting a barbell. How much work is done in lifting a barbell that is twice as heavy as the first one, but you're lifting it the same distance? Well, we can say that work. Okay, so we have the work is equal to the force times the distance. If the force goes up double, because if the weight becomes twice as heavy, it's going to take twice as much force to lift it, then you're going to end up with needing twice the force to lift it. In other words, the work is going to take twice as much force times the distance. That originally it was force times distance, now it's 2 times the force times distance. That means that it's going to be twice as much work. And so the answer is that it's going to take twice as much. Now what about if you're pushing a cart, you use the same force, but it goes twice as far, so the distance is twice. How much work would be done compared to the case of going half the distance? Well, if you go twice the distance, remember, work is simply force times distance. Work is force times distance. If you double the distance, that means you're going to double the work. And so it would again be twice as much. Now, work is related to something called energy. In fact, energy is sometimes called the ability to do work. That means that energy is the ability to apply a force to something and move it over a distance. And so we can say energy is equal to the ability to do work. Now, basically, that's the physics definition of energy, but what does that mean? Another way that we can define energy is one that can make it more sensible to us. And we could also define energy as saying that energy is defined as that which produces a change in matter. And so if energy is the ability to do work, in other words, energy is the ability to apply a force to something and move it over some distance, that's going to be something you can do to move matter around or change the way matter interacts. And so that's why we can say that energy is defined as that which produces a change in matter. Now, the effects of energy are only observed if it's being transferred from one place to another or if it's being transferred from one form to another. And both work and energy are measured in units called joules. And 1 joule is equal to 1 Newton times 1 meter. Because work is a force times distance, work is a force times a distance, and so here we have work is force times distance. Remember, the units of force are newtons, the units of distance are meters, so the units of work, which is a joule, 1 joule would be 1 Newton times 1 meter. Now, if I move a block from one position to another position, I can apply some force to it, and the force is going to be applied, and I can have that force be applied over the distance. Now, I can move that block fast or slow. In other words, the amount of time it takes for the block to go from where it starts to where it ends up can be different, depending on how fast the block is moving when I apply the force. So, what that means is that you can get the same amount of work delivered, but the time over which the work is delivered changes. And so that causes us to want to define a new idea, and that idea is something called power. And power is a measure of how fast work is done. And the equation for power is very simple. You simply take the work, you calculate the work, and you divide by the time. So power is equal to work over time, or energy over time, because work and energy are related. And so that's the definition of power. Now, energy can be different forms. Energy can take different forms. And one example, one type of energy is called potential energy. And so let's say that I take a ball and I lift it up against gravity and I move it up some height. In each of these cases, I've moved the ball up 3 meters. But in one case, I've lifted it straight up and then rested it on this pole here. And the other case, I've pushed it up a hill. Now, it's the same height. It's going to be 3 meters there. And if you remember from your high school, if that's 5 and that's 3, that's going to be 4. So it's going to go 4 to the right, but it'll go 3 meters up, and it'll go along the hill 5 meters. But the key thing is it's going the same height. So here it goes 3 meters, there it goes 3 meters. And even if you lift it up a staircase, you push it up there, it rests, you push it up there, it rests, you push it up there, it's still had the same height. Now, which way is the force of gravity working in all of these cases? Gravity is working straight down. So the motion is in the same line as gravity. So we can say that gravity is doing work on this ball. And the amount of work that gravity does on this ball is the same amount regardless of these 3 cases. Because remember, side-to-side motion doesn't matter, only motion along the direction of the force. Now, what happens to the work that I did on this ball to move it up 3 meters? That work goes into what we call potential energy. And you can think of it as stored energy. And so what's going to happen if I nudge the ball, if I kick the ball right there, it's going to fall back down. If I kick the ball here, it's going to fall back down. The And what happens as it falls is it's going to speed up. And so that potential energy gets converted into motion, into the energy of motion. So here we have potential energy. Now, potential energy is defined as stored energy due to position, shape, or state. And in its stored state, the energy has the potential for doing work or to be converted into motion. Now, some examples of potential energy are a drawn bow. So if you take a bow and arrow and you stretch, you draw the bow, you have used work, you've done work to stretch the string of the bow, and then when you let it go, the potential energy that you put into the string of the bow, the stored potential energy is released, and the string snaps back and it pushes the arrow forward. And so by drawing a bow, you're doing work, and your work is going into creating potential energy. Same idea with a stretched rubber band. You stretch a rubber band, you let it go, it contracts. That stored potential energy converts into motion. We can see this same idea with the raised ram of a pile driver. So if you have some object that's been lifted up some height, it's been lifted up against gravity, and then if you let it falls down, and that potential energy is converted into motion again. So this is the basic idea of potential energy. It's stored energy that can be converted into some kind of motion. Now, there are different types of potential energy, and the one that we're going to focus on is called gravitational potential energy. And it's basically, it happens when you do work against gravity. And so you've got some object and you lift it up so that it is raised some height, and you have to apply some force to lift it up. Force times the height, or force times the distance it moves, that's going to be the work that you do. But at the same time that you're lifting it up, gravity is pulling it down. And so gravity is also doing work against the box. And this is what causes it to have stored energy. Now we can actually write, because how much force do you have to lift up with? You're going to have to lift up with the force that equals the force of gravity. And so gravity's pulling it down, you lift up, you have to match the force of gravity. And we know that the force of gravity is simply the weight, which would be the mass of the object times little g, the acceleration due to gravity. And so, if you multiply this force, which is the weight, mg, times the distance, which is the height, that gives you the gravitational potential energy. And so, whenever you want to calculate gravitational potential energy, that's the formula that you're going to need to use. And so, if you want to calculate it, this is the formula that we're going to use, that potential energy is the weight of the object times the height the object is lifted, or in equation form we can just simply say it's mg times h, where m is the mass, g is the acceleration due to gravity, and that's about 10 meters per second squared. The actual number is 9.8 meters per second squared, but close enough to 10, good enough for government work. And then we can say that h is the height. And so that's the formula for calculating gravitational potential energy. And basically anything that you lift up is going to be against gravity is going to be given gravitational potential energy. And so here are some examples. Water in an elevated reservoir. You pump the water up to some height, and then the water can fall back down. Or again, we talked about the elevated ram of a pile driver. You lift it up, it's going to be able to fall down. That is the basic idea. You have this gravitational potential energy that you've done. You've given it the gravitational potential energy by doing work to lift it up. That's where the work that you do goes. So you apply some force to some object, some force gets used to lift it up, and that force times distance, that is the work that you do that gives it gravitational potential energy. So when you let it go and it falls, gravity can pull it back down and convert that energy back into motion. Now we want to talk about a very important principle in physics, the idea of the work-energy theorem. And this can apply to increasing speed and it can apply to decreasing speed. Now the example that is commonly used for decreasing speed is when you have some kind of friction. So for example, if you have a car and you hit the brakes on the car, the braking causes there to be more friction, and that reduces the energy, and it causes the car to slow down to be basically slow down until it stops. Now, the next topic that we want to talk about is kinetic energy. And kinetic energy is defined as the energy that a body has because it is moving, the energy of a moving body. And the equation is the kinetic energy is equal to 1/2 times the mass times the speed squared. And remember, when you square something, that means you just multiply it by itself. And in a formula form, you would say that it is 1/2 times the mass m times the speed or the velocity squared. And so 1/2 mv squared, that's the formula for calculating the kinetic energy. And again, that's the energy anything has when it's moving. So here's the full form of the work energy theorem, and this is the part that you need to know. When the work done on an object changes the kinetic energy of the object, the amount of work done is equal to that change in kinetic energy. That means that the work, which is the force times the distance, and again, this is the work, that's equal to the change in kinetic energy. And that means the final kinetic energy minus the initial kinetic energy. And of course, that's going to be 1/2 times the mass times the speed squared, but it's going to be the final speed squared minus 1/2 mvi squared, and that's 1/2 the mass times the initial speed squared. And so this is the change. And so the key things here that we want to look at are the force times the distance, that's the work, and 1/2 mv final squared minus 1/2 mv initial squared, that's the change in kinetic energy. So the two things I've circled in red here, that's really the work energy theorem. The force times the distance equals 1/2 mv final squared minus 1/2 mv initial squared. Now we can put all these ideas together. So this fundamental principle of nature is called conservation of energy. And basically what conservation of energy tells you is that energy is neither created nor destroyed, it simply gets transformed from one form into another. And so here we see an example. We have this, I don't know if you can see, this is like a winch here that's basically attached to a rope that goes over a pulley, and by turning this crank you can lift a body up. So this rope is pulling this guy up over the pulley, and so the force in the rope is lifting it up, so you do work that gives it potential energy. And then if you cut the string, what's going to happen is this guy's going to fall back down, and so as it falls, it's speeding up and it gains kinetic energy, the energy of motion. Just to say that again, just to be clear, you've got three things going on. First, you lift this guy up, so you do work to lift it up. That gives it potential energy. So you've converted your work into potential energy. Then you release the rope, and the object's potential energy gets converted into kinetic energy. In all of these cases, the amount of energy or the amount of work is going to be the same. It's just transformed from one form to another. And by the way, you don't have to go to potential energy first. If I have just a regular block and I apply a force to that regular block, what's going to happen is that block's going to accelerate. It's going to speed up. And so 1/2 mv initial squared is going to go to 1/2 mv final squared. Oops, that should be squared there. And so the work, the force times the distance, is equal to that change in kinetic energy. And that's what the work energy theorem tells you. So when you do work, it can go into potential energy or it can go into kinetic energy. If you have kinetic energy, it can turn into potential energy. If you have potential energy, it can turn into kinetic energy. But the total energy is conserved. And that's the key concept. That means that the energy may transform from one form to another, but the total amount of energy you have stays constant. Okay, so we've covered some basic ideas about momentum and energy, and both kinetic energy and momentum have to do with motion. And so remember, momentum has the formula mv, and kinetic energy has the formula 1/2 mv squared. And so both depend on the mass and the velocity or the speed. But there are some important differences. Now, the first really big difference is that the kinetic energy depends on the square of the velocity or the square of the speed, whereas the momentum depends just on the velocity or the speed itself. And also, we can note that momentum is a vector quantity, so sometimes we'll write an arrow on top of the v to remind us that it's a vector, and that kinetic energy is what we call a scalar quantity. It's just a regular number. There's no direction. With momentum, the direction matters. So remember, with momentum, you could have an object going this way, mv, and you could have an object going this way, and that would be minus mv because the velocity was in the opposite direction. It would be negative. But when you square a negative, you end up with a positive number. So you can't have a negative kinetic energy because the direction doesn't matter. It's a scalar quantity. Now, that is some of the big differences between kinetic energy and momentum, even though their formulas are very similar. And just to recap the very important principle of conservation of energy, in everyday language, when we talk about conservation, like conservation in nature, we mean to save something. But in physics, the word conservation has a very specific meaning, and it means the total doesn't change. Now, the individual parts can change, but the total stays the same. And so here is the way that we generally write the law of conservation of energy in physics. We say, in the absence of an external work input or output, that means a force acting over a distance, that's what a work input or output is, the energy of a system remains unchanged. Or an easier way, if I ask you on a test, what does conservation of energy tell you? It tells you that energy cannot be created or destroyed. And I'm going to add to this PowerPoint slide, but it can be transformed into a different kind of energy. So for example, you could have kinetic energy transform into potential energy, or you could have potential energy transform into kinetic energy. You could have kinetic energy transform into heat energy, which is another kind of energy we'll talk about later. You can transform energy from one kind to another kind, but the total amount of energy you have is going to be conserved. In other words, it's going to remain unchanged.